ever just stop and wonder how our crazy, complex world, well, works? I mean, think about it. Planes stay in the sky, the power in your house is always on. There's gotta be something behind the scenes, right? Some kind of invisible brain making sure everything runs with perfect precision. Well, in this explainer, we're gonna pull back that curtain and see exactly what makes this invisible brain tick.
You see it up in the air, right? High-performance jets pulling off maneuvers that, honestly, no human pilot could handle on their own. It's just incredible.
And you see it down on the factory floor. We're talking whole teams of robots working in perfect sync, building the stuff we use every single day, with mind-blowing speed and accuracy.
We even see it way out in the vacuum of space. Robotic arms doing these super delicate, complicated jobs hundreds of miles above our heads. Just think about that.
So, how on earth is any of this possible? What is this invisible secret that's holding our entire modern world together? Well, the answer is a concept that's both super simple and unbelievably powerful: automatic control.
To really get how important this is, let's just imagine for a second. A world without it. What would happen if this invisible brain just switched off?
The results would be, well, instant chaos. Power grids would collapse, plunging everything into darkness. Modern airplanes, they'd literally fall out of the sky. Even the basic systems in our own bodies, like regulating our heartbeat or our temperature, they just stop working.
This quote from one of our sources really puts it in perspective. It says that without automatic control, you wouldn't even be alive long enough to finish this article. So we're not talking about a convenience here. This is absolutely vital to our very existence.
Okay, I know that sounds pretty intense, but the core idea behind all this complexity is actually something you do every single day without a second thought. Because, get this, you yourself are an amazing control system.
Let's break it down with a simple example. Picture this. You're on a motorcycle. Your goal is to get from 0 to exactly 60 miles per hour. How does your brain actually pull that off? Well, your brain is running this constant loop. First, you set your goal, 60 miles per hour. Then you sense where you are right now by looking at the speedometer. It says 0. Your brain instantly calculates the error. The gap is 60. So you act, you twist that throttle hard to get going. But here's the magic part. As you get closer to 60, you're doing this over and over, sensing the smaller error and adjusting your action by easing up on the throttle. That final bit, that's called feedback.
That whole process, that feedback loop, is the absolute key to everything. Now let's see how that intuitive thing you just did translates directly into a fundamental principle of modern engineering.
Okay, this is where it gets really cool. We can actually map your actions directly onto the components of an engineered system. Check it out. Your eyes reading the speedometer, that's the sensor. Your brain comparing your speed to the goal and deciding what to do, that's the controller. And your hand twisting the throttle to change the fuel flow, that's the actuator. Sensor, controller, actuator. Your eyes, your brain, your hand. These three parts are pretty much the building blocks of every automated system you can think of.
This whole thing is what engineers call a closed-loop control system. The name says it all. It's a loop. It's not just a one-and-done command. The system is constantly using feedback, that information about what's actually happening, to compare it against what it wants to be happening, and it's always working to get that error down to 0.
So if you remember just one thing from all this, make it this simple cycle. You sense the current state, you think or calculate the error and decide what to do, and you act to fix it. That is the invisible brain in action.
But how does the think part actually work inside a machine? How does a controller figure out how much to act? Well, it uses this surprisingly simple and elegant algorithm that's been the workhorse of industry for like 100 years.
It's called PID control. That stands for proportional, integral, and derivative. Now, don't get hung up on the math. The concept is what's brilliant. These are just 3 different ways the controller looks at the error to come up with the perfect response.
Let's start with P for proportional. This one is simple. It looks at the error right now, in the present. If the error is huge, like you're at 0 but you want to be at 60, it gives a huge response. Twist that throttle hard. This is the main muscle. Next up is I for integral. This one looks at the past. It asks, hey, has there been a tiny annoying error that's just been hanging around for a while? Maybe you're stuck at 59.9 miles per hour. The integral part adds up that little error over time until it builds up enough oomph to finally nudge the system that last little bit to 60. It's all about getting rid of those stubborn, lingering mistakes. And finally, D for derivative. This one is super clever. It tries to predict the future. It doesn't care about how big the error is, but how fast it's changing. So if you're rocketing towards 60 miles per hour, the derivative part yells, "Whoa, slow down, we're going to fly right past it." It's like a brake that smooths everything out and stops you from overshooting the target.
And by mixing and carefully tuning these P, I, and D values, engineers can take a system that's all over the place and totally unstable and turn it into something optimal, something that hits its target fast, with perfect accuracy, and no wobble. That perfect balance, that's the real magic of PID.
In this whole idea, this simple feedback loop, it not just for motorcycles or the thermostat on your wall, it is the absolute foundation for solving some of the world's biggest, most complicated challenges.
The very same logic that guides your hand on a motorcycle throttle gets scaled way, way up to manage gigantic chemical refineries and even entire power grids for a whole continent. It's what keeps them running safely, efficiently, and reliably 24/7.
The impact is literally everywhere. It's why our cars are getting safer and way more efficient. It's what makes those automated factories possible, what keeps our power and communication networks from failing. It lets us explore deep space in the bottom of the ocean. It's even inside advanced medical devices, like pacemakers, that are keeping people alive right now.
It all comes back to that simple, powerful loop. Sense, think, act. It's the basic building block for anything autonomous. And that leaves us with a really fascinating question to think about. We've pretty much mastered this loop for cars and factories and power grids, so what's the next huge problem that humanity is going to solve by teaching a machine to just sense, think, and act better than we ever could?